Welcome back, everybody. So we're in 10.2, which is entitled Direction Fields and Euler's Method. So our focus is going to be on Euler's method. We've looked at direction or slope fields before, but we're going to look at this additional method called Euler's method for approximating a solution. That's going to be a little bit more accurate than our approach that we took last year. So last year, when we looked at slope fields, and we were asked to sketch a graph of the particular solution, we essentially would take our curve, look at the given point. So here we've got 0, 1 is the coordinate that's given. And then we would approximate based on our slope field. So we would try to match our slopes to that curve going in both directions. All right, so maybe this would be our approximate solution of a curve. And note it's defined by two variables, right? So we've got two variables, so our slopes depend upon both x and y here, so it's not a solvable differential equation for us. And all we have is this initial condition in the slope. So what we're going to look at today is a method called Euler's method that's going to allow us to sketch this graph much more accurately. And really what we're going to focus on is working through the iterative process, but in reality, Euler's method would be something that a calculator would be used to calculate. You could easily work a lot of these out using like an Excel spreadsheet where you're typing in formulas as well. And it's a really neat method for approximating a solution curve point by point where you're using really small increments between each point. So let's go ahead and get into what Euler's idea was. So what Euler decided to do was take a given value, so if we're just looking at the picture here, and then go some distance away from it, which is typically denoted with h. You could also call it delta x, and approximate the next location of where that point would be by looking at the slopes. So let's go ahead and go back a little bit to Calc AB, just to kind of look at our notation here. So we know that for our solution curve, which looks like y equals f of x, the rate of change of y with respect to x, which we call the derivative, we call, f prime of x or dy over dx. And for us, this dy over dx expression is going to be more useful for our notation, because what this derivative equation implies is that dy, that distance between our two y values in our curve for that slope of the secant line, that infinitesimally small length dy is equivalent to the derivative of our function times dx. So now let's add in kind of a picture here so we can see what's going on. So suppose we had some curve here. So if we're looking at a point on our curve, let's say it's here, we'll call that x. And let's go some distance away, let's call that x plus delta x. You could also do x plus h. So we've got those 2 points. So now dy over dx was defined as a limit. So the limit as delta x approaches 0, f of x plus delta x minus f of x, all over x plus delta x minus x, which simplifies to just delta x. Note, sometimes we use the letter h as well for these. And note, what this limit tells us is that this top expression, the difference of the y values, that's our dy. And then delta x, as delta x approaches 0, becomes dx. Right? So both of those values are shrinking towards 0. So on our picture here, right, if we zoom in a bit and we use maybe different color, that means that if we're looking between those 2 points, then if we're looking at that slope of that secant line expression, what we get here is delta x and delta y for those infinitesimally small lengths, right? So this is just some finite length. that we've chosen here, but we're going to shrink this triangle down so that the triangle is essentially 0. And so what we end up with is as delta x goes to 0, delta y becomes dy, and delta x becomes dx. But delta y, if it becomes dy, is the same as or equivalent to f prime of x dx. So if we're thinking of our slope triangle in terms of differentials, what we get is dx and then f prime of x dx. And so that vertical and horizontal relationship is what Euler used to approximate the next point on our curve. So if we start here, we can approximate our next point by considering these two ratios, or these two lengths. Okay, so let's go ahead and go back here. So we've got that picture kind of drawn for us here. And note, we're still approximating, right? So there's going to be some difference in the actual values, right? So we're not getting the exact solution curve, but we can't solve it algebraically anyway with the integration process. So we really have to kind of do it as an approximation. So note, even though we are approximating, there's definitely going to be some error involved. Okay, so let's look at how we're going to work this through. And it kind of shows you on the right-hand side what's happening, which is over here. So essentially what we're going to do, if we kind of zero in, is we're going to start at some value x naught, y naught. So we're going to have some initial condition. And to get to our next y value, we're going to move some small distance h, right? So note, for the next coordinate, we'll have x naught plus h, comma y1 is what we want to get. And to get y1, we'll take our initial value, and we're going to add that vertical length, right? Delta x times f prime of x. So note this vertical length here. But we write it as f of x 0, y 0 because a lot of times our derivative is going to be dependent upon both variables. So we'll just note this f of x naught, y naught is just the derivative at x naught, y naught. All right. Sometimes it's written with like a capital F also, just to make it look different from the actual function value. It's kind of wonky notation, but it's the one our textbook uses, so we'll kind of stick with that. But no, that's really just the derivative value. And then, to get the next value, so y2, that's going to be x naught plus, well, 2 h's, right? Whatever our chosen step length is. And note, h is sometimes called the step length or the step value. And then we'll get y2. So, meaning we'll take the value that we approximated previously and do the same process. Add that vertical distance of h times the derivative of f at x1, y1. And then we'll do the same thing for y3, y4, y5, and we can iterate forever. We can continue on forever. So let's go ahead and just jump into some examples here. And note what we're going to want to use is kind of a table. It doesn't have to be like super sophisticated like this. So note, I'll kind of simplify a bit. But this is essentially going to be what it looks like in general for our iterations. So let's go ahead and look at our first example so we can see what this will actually look like in practice. So use Euler's method with step size 1/2 to compute approximately the first 4 iterative values using Euler's method. So we've got the initial value problem is given as y prime is y minus 2x, and y1 is 0. So if I'm starting with my table here, xn, yn, that's going to just be my initial values. So I'm going to start with the coordinate 1, 0. And then I'm going to compute y prime at that value. So we'll just note this is pretty easy to calculate, but just in case. So we've got 0 minus 2 times 1 which is negative 2. So y prime is equal to negative 2. What I didn't write here that I should have maybe is that h is 0.5. Right, that's our step size. So then to get our delta y, the value we're going to add to our initial value here, that is going to be equal to h times what we just computed in the previous step. So now delta y is 0.5 times negative 2, which of course is just negative 1. So then y sub 1 is going to be equal to 0 plus negative 1, which is negative 1. Which means now that once I move to my next step, 1.5, I'm going to use the y value, negative 1. Okay. And then I'm going to repeat the process. So for y prime here, we're going to get negative 1 minus 2 times 1.5, which is negative 1 minus 3, which is negative 4. For delta y, we're going to get 0.5 times negative 4, which is equal to negative 2. So then y sub 2 is going to equal negative 1 plus negative 2, which is negative 3. So now I've got negative 3 at my next step. And so note, we want to go to y sub 4, so that's going to be for 2.5 and 3. And just note, you can fill in the x values first if you want to. You can just fill them all in because they are just going to be fixed by h, right? So we're just adding h each time to get our x values. So for the next value, we've got 2, negative 3 is our approximate location. And so then our y prime is going to be negative 3 minus 4, which is negative 7. So then delta y is going to be half of negative 7, so negative 7 halves. And then we'll add that to our value of negative 3. So y sub 3 is going to be negative 3 minus 7 halves, which is negative 6.5. Yeah. And then we'll do it one more time to get our fourth iterative value. So we're going to have 2.5 and 6.5. So our numbers are going to get a little messy here. So we'll have negative 6.5 minus 5. So we get negative 11.5. So then delta y, our distance moved, is going to be half of that. So let's see, that's 23 over 2. So half of 23 over 2 is going to be negative 23 over 4. Let's double check that with a calculator. Yes, okay, so then y sub 4 is going to equal negative 6.5 plus negative 23 over 4, which is 5.75. So that's going to give us negative 12.5 for our final approximate value. All right, so we'll just note here what we've done is, we've got our x naught, y naught that we started with. So our curve is definitely going to pass through the coordinate 1, 0. And then what we're going to do is look at approximately how it's changing by using this iterative slope approximation. And so if we graphed these values, these would be the first 4 points based on our approximation. And again, these aren't the true values, and there's going to be plenty of error included in these. So you could kind of imagine if we really wanted to get an incredibly accurate graph, we need to make h really, really small, right? So maybe we want h to be 0.01 in reality if we were going to do this with a calculator. For us, because we're just introducing it though, we're going to use kind of nicer numbers in general. But a real use of Euler's method is going to use really small step sizes to approximate values. All right, so that's our first example. So let's go ahead and jump into the second. So for this, I kind of left it blank. I'll let you decide how you want your table to look, if you want to build a table at all. So we want to use Euler's method with 5 equal steps to compute the approximate value of y of 0.5, where y of x is the solution to the initial value problem, y prime equals y plus xy, and we know that y of 0 is 1. So note we want 5 equal steps. So if we're starting here, we're going to have 0, 0.1, 0.2, 0.3, 0.4, 0.5. Clearly, h is 0.1. So we've got our 5 steps here. And we're going to end with our approximation. Oops. And these values are not going to fit, it looks like. Let me fix my table a little bit here. So note, be careful, these can get messy. Okay. So we'll try our best here to see how non-messy we could make it. I'm going to create some space for y because we could have some messy numbers. Definitely use a calculator for these. So these are going to be examples where you can definitely use a calculator. All right, so let's delete that and let's jump into it. So we need our y prime values. And then we're going to have delta y, which is h times y prime. And then we'll have our new y value. So maybe y old plus delta y. All right. So let's go ahead and calculate. So y prime for our initial expression. So we've got y, so we'll note this is y plus xy. So x is 0, so the xy cancels, so we'll just have 1. So then delta y is going to be 0.1 times 1, which is 0.1. So then our new value is going to be 1 plus 0.1, which is 1.1. Very nice. So a nice initial value here. So 1.1. All right, so now we're going to use this with our next iterative value. So we're going to have decimal points here. So we're going to have 1.1 plus 0.1 times 1.1. So we get 1.21. So again, definitely use a calculator for these. We're going to multiply that by 0.1. So we're going to get delta y is 0.121. So then we'll have 1.1, our previous value, plus 0.121, and we'll get 1.221. Good. So then for our next value, we're going to have 1.221 plus 0.2 times 1.221. So we get slightly larger number, 1.4652. For these, try to use all the decimal places for as long as you can to get the most accurate. Your final answer needs to be correct to 3 decimal places, but your intermediate work should use all decimal places in your calculator. So then times 0.1. So now we're just going to move a decimal place since h is 0.1 or 1/10. And then we'll add that on to 1.221. And we get 1.36752. So got 2 more to go. Almost there. So we've got 1.36752 plus 0.3 times 1.36752. So we're going to get 1.77, lots of sevens, 6, delta y, 0.177776. And our new value is going to be adding that on to 1.36752. So we get 1.545, 2976. And we'll do one more step here. Oh, sorry, 2 more steps. No, sorry, one more step. Forgot to fill it in. All right, so one more step to get our y of 0.5. So let's go ahead and calculate the derivative. It's going to be that number plus 0.4 times that number. So the answer key in your calculator is going to be very useful because then you can just recall it as opposed to retyping it in. So we get 2.16341,664. So delta y is going to be 0.216341664. So then our approximate value is going to be 1.761639,264. And again, we can use the whole number, the first 3, up to 3 decimal places or more. So 1.761, again, would be perfectly fine, but we could add a couple more approximate values if we wanted to. So really for these examples, it's going to kind of repeat this process over and over again. So there's a couple of additional examples here below that I'll let you do on your own, and then you can check the completed notes online. All right. So again, if you have questions, shoot me an email or come by the office hours otherwise.